So in geometry and in quite a bit of upper level math, you're no longer going to be just finding an answer. You're actually going to be proving that something is true. It's a lot more logic based and a lot less about the calculations, although you may do some calculations within that proof. There are many ways to prove something is true, and this applies to lots of fields, like in a courtroom. You might have to prove your client is innocent, or all sorts of different places. But in math, a proof always starts with a basic principle or definition or some information that you're assuming. We call it like what's given to you, the given. Then you're going to include some sort of reasoning, and that will differ based on the proof. And then you need to make a conclusion. So if you were trying to prove the two triangles are similar, you need to conclude, okay, so the two triangles are similar based on this reasoning. Just by the way, when we get to the end of a formal math proof, to indicate that we've reached the end, you typically write a little square, or you can fill it in if you want. Or some people write QED. This is more upper level stuff, but I just think it's fun. QED stands for a Latin phrase, quod erat demonstrandum, which basically means I proved what I was supposed to prove. Technically, it translates to that which was to be demonstrated. It's like mathematically dropping the mic, like, boom, proved it, I'm out. One common way and very simple way that you can prove something, it's called modus ponens. Again, this is a Latin word that means the way that affirms by affirming. Basically, you start with some basic assumption, like if A, then B. For example, if we win the football game, then we go to the next round of playoffs. Then your proof would be showing that A is true. So like, we won the football game, therefore we conclude that we go to the next round of the playoffs. So you start with this if statement, you say that A is true, and so therefore you can conclude B. That form of logic has the name, it's called modus ponens. It seems like common sense, but it makes logical sense. That's the whole point. There are other ways to prove things, though. Here's another example of modus ponens. So like, if you have the password, then you can log onto the computer. You don't have the password, therefore you cannot log onto the computer. So kind of doing it backwards. And there's a name for that, but we won't get into it. Here's another example of modus ponens, and you've actually already kind of done it. If two angles of a triangle are congruent to two angles of another triangle, then the triangles are similar. This is the angle-angle property that we've talked about. And so then my proof here would be like, okay, well, angle B is congruent to angle E, and angle A, well, you'd have to do some subtract from 180. So if I subtract this and subtract this from 180, oh, these actually are not the same. If you do 180 minus 60 minus 81, you get 39. And if you do 180 minus 40 minus 81, you get 59. Those two angles are the same, but these angles are not. And so angle A is not equal to angle F, and it's not equal to angle E either. And so this is not true. They are not congruent. So you could say triangle ABC is not similar to triangle DEF. Okay, here's another one of those. So it's given that DE and AC are parallel, and I want to again prove the triangles are similar. Bit of a side note, I know that these angles are the same because if I have two parallel lines with a line cutting through it, you know that these corresponding angles are the same. So that's what they use in this proof. Basically, angle B is congruent to angle B because it's the same angle. We call that the reflexive property, by the way. And then we can say BDE, so BDE here, is congruent to angle A, and that's because they're corresponding angles with parallel lines. And so because of that, I have two pairs of congruent angles. So then I can conclude that the two triangles are similar. The reason being because of that angle-angle property. This is modus ponens. It's like, if I have two congruent angles, then they are similar. I proved I have two pairs of angles, therefore they are similar. Proofs don't always have to look like this. So writing your proof in two columns can be a good way to organize your thinking. Like, here's a statement, but you have to have justifications for those statements. So like, how do I know that these are congruent? I know that because of this reason right here, because they were corresponding angles. How do I know they're similar? Because of the angle-angle theorem. So you need to have reasons for your statements to make it a good proof. But it doesn't have to be written like this. So the more advanced you get, the more your proofs will look a little more just like paragraphs. For example, you don't really need to understand this, but I think it's a pretty interesting and fairly straightforward proof. What they do is they start by giving you a theorem and you have to try to prove it. So like, this is almost like the answer that you're trying to get to. So we want to prove that the sum of two even numbers is an even number. Like 2 plus 4 is 6, still an even number. So the proof here is basically, if you have two even integers, they have to be multiples of 2. So they're going to make it 2x and 2y. And so if you add them up and then factor out the 2, you get 2 times x plus y. And this is basically also an even number because it's 2 times a number, so we know that it's even. And so that's pretty much the proof. And like I said before, look, put a little square at the end to be like, I'm done. That's the end of the proof. Just to be a little silly here, I'm going to prove that girls are evil. You ready? This is obviously a joke and a little bit sexist, but anyway, here we go. So, we all understand that girls equal time and money. You know, that's what I hear anyway. And we also know that time is money. People say that sometimes, time is money. And so we could do a little substitution here. Substitute money in for time, because it equals time. So girls equal money plus money. Oh, sorry, this was supposed to be multiplication. Oh, I messed it up. It's ruined. Money times money. Money times money is money squared. So girls equal, you know, money squared. Plus we also know money is the root of all evil. So the root of all evil. And so if we were to substitute this in for money, we could conclude that girls equal money squared, except for money, we're going to put the square root of evil squared, which is just evil. So here we go. Girls equal evil. Boom. QED. I'm done. Like I said, that's pretty dumb. But it is a good example of kind of how proofs work. You start with understandings. Usually they're not stupid like this, but like axioms or understandings that everyone agrees with. You do what I call a little razzmatazz in here, whereas you do a little math to prove your point, and then you land with what you were trying to prove. I want to show you one other random proof written as paragraphs. You don't have to, again, worry about understanding this completely. If you want to read through it, that's great. This is a proof that the square root of 2 is an irrational number. So like I said, they're going to conclude with that. They're going to conclude, therefore, the square root of 2 is an irrational number. Put your little square that you're done. This is an interesting proof, and this is actually a common way of proving things, but the way they proved this is they actually assumed that the square root of 2 was not irrational. This is called proof by contradiction. You actually start with assuming that the opposite is true. You show that that doesn't work out, And so if that doesn't work out, then it has to be the opposite, that square root of true is irrational. So that's kind of an interesting way of proving things too. All right, in the next video, we are going to do some proofs of the Pythagorean theorem.